I'm Simon Perrault, and I will be the chair for this session. I'm very happy to see so many people. I would like to apologize. I tried to have this session planned at 1 p.m., but unfortunately we have to get it very early in the morning, so thank you for coming. This session will be especially exciting because we have a lot of honorable mention. So the first talk will be SkinTrack by Carnegie Mellon, and will be presented by Zhang.
Thanks for the intro. My name is Zhang. I'm a PhD student at Carnegie Mellon University. Today I will talk about the project called SkinTrack. This work has been done with my colleagues Junhan, Gierad, and my advisor Chris Harrison. As we all know, smartwatches are small but powerful computers. However, in the case of smartwatch, the screen is so small, while our fingers are big. So we wondered, can we spill interactions out onto the surrounding skin? And how to do it efficiently and robustly? We are not the first who considered this interesting possibility. A lot of previous approaches has been tried. For example, the most intuitive way is to put a touch-sensitive overlay on top of the skin. However, it's always desirable to use remote sensing and avoid instrumenting our skin directly. For example, people use bioacoustic vibrations to localize finger touches and detect directional swipes. However, this approach is very low resolution. The only work we saw that can support continuous finger tracking use camera worn on the shoulder. As we can see, it's quite obtrusive, and it needs a clear line of sight to our skin. Lastly, we use a proximity sensor to enable discrete touch buttons on the skin. However, this approach only detects 4 touch locations. Through this previous work, we can come up with some ideal sensing properties. First, it should support continuous finger tracking. Also, it should not depend on a clear line of sight to the skin. And it should be non-obtrusive, and ideally, it can be integrated into a smartwatch. We developed a small touch tracking system that we attempt to achieve all of the above sensing properties. We call this system SkinTrack. As we can see in this image, SkinTrack has 2 components, a signal emitting ring on the right and a sensing band. Before I talk about how the system works, let me first explain what the physics behind. Our sensing principle is based on the fact that electricity takes time to travel. In the case of electrical signal, it will reach different physical locations at different time, even though this time latency is very small. But in the case of high frequency signal, it will result in observable phase shift. And in the case of human body, the skin has a dielectric constant of 17. That means if we have a 80 megahertz AC signal, it will travel through our skin with a wavelength of 91 centimeter. And each centimeter it travels, it changes phase by roughly 4 degrees. We conduct a very early experiment to verify this. Here is the setup. So we put a signal emitting ring to the finger. The signal propagates out of our finger and radiates out through the skin. It is then collected by the 2 electrodes. So on the oscilloscope, the yellow signal is collected from the left electrodes, and the blue signal is collected from the right electrode. The difference between these 2 signals is shown in purple. We can see the phase difference between these 2 signals, but more importantly, the phase difference changes correspondingly to finger movement. And here how it works in SkinTrack. We put a signal emitting ring shown in yellow, and first 1 pair of electrodes shown in red. When the finger touches on the skin, note the distance between the finger and the 2 electrodes are different. This results in an observable phase difference. When the finger moves to a next location, the phase difference changes. This can be used to detect Y position of the finger. Now we add more pairs of electrodes to be sensitive to X-axis movement. With this 2D tracking ability, we can power interactive applications. For example, we can draw an amp to quick launch a music app. We conducted a series of experiment to verify our sensing principle. Here, we draw 7 dots on the user's wrist along the wristband, and we compare what we measured with our predictions. So in this chart, the red line is based on our theoretical model, and all the blue dots is what we measure when we touch on these 7 dots. As we can see, these 2 signals matches each other pretty well. Here's also another experiment when we move the finger horizontally along the arm. Again, these 2 signals matches pretty well. Even though we still see mismatches between the 2 signals, that is because the electrode we use are copper patches instead of the absolute point we assume in our model. And also our arm is pretty curved. It is not absolute homogeneous, which makes the signal propagation more complicated in reality than in theory. Now I'm going to show a live demo of SkinTrack. So here is the wristband of SkinTrack. As we can see, there are several electrodes underneath. I'm going to put it on my body. Because different users have different body, SkinTrack has to be calibrated per user. So I want to show you how this calibration is done. Now I'm going to put on the signal emitting ring. So as we can see, when I touch on my skin, the signal changes dramatically. So we have a classifier whose only job is to detect whether there's a finger touch on the skin. And this data is fed to that classifier. So now I'm going to calibrate this system real quickly. Okay. I'm going to touch on these 9 crosshairs sequentially. So now my finger is away from the skin, so nothing shows on the screen. When this hover, it shows. And then I'm going to touch, move to the right, to the left, up, and down. I'm going to draw a circle. Hover, and then away. As we can see, I only trained this system very quickly, but it should give you an idea with the accuracy of SkinTrack. So that's my live demo. Now let's talk about how we made this. To give a little bit more detail about SkinTrack, we use an oscillator powered by a battery to make our signal emitting ring. So as we can see, this it uses a fairly big battery, but it gives us a 15-hour battery life. As I will tell a little bit more at the end of this presentation, there are always ways to shrink this battery. Now for the wristband, we use 4 pairs of electrodes. 2 pairs of them are sensitive to X movement, and the other 2 are sensitive to Y movement. We use 4 phase comparator chips. Each of them takes input from 1 pair of electrodes. It outputs voltage to indicate the phase difference between the 2 signals. These voltages are then sampled by this Atmel microcontroller and then sent to a laptop through Bluetooth Low Energy for further computation. We conducted a user study to evaluate SkinTrack. It involved 12 participants. As we can see, a smartwatch naturally segments a user's arm into 4 locations. They are front and back of our arm and front back of our hand. We evaluated SkinTrack on all 4 input locations. For each input location, we collected 3 training rounds, then followed by 3 live testing rounds. Then we asked the participant to remove the wristband, relax, and put it back on, followed by 3 another testing rounds. I'm not going to go into detail about this, but in short, we collected 3 touch states. They are finger out of range, hover, and touch. In total, we collected more than 100,000 test instances, all labeled in real time. And here is our result. The result I'm going to talk about here are all generated in real time by live classifier. For touch state detection, here is the computer matrix. It shows that SkinTrack is able to detect these 3 touch states at 98.5% accurate. If we only care about touch and not touch, we can, just like a touch screen does, we can combine hover and out of range together, and that accuracy is even higher. For touch tracking accuracies, here are the 4 input locations, and each location has 9 crosshairs. So we rendered all touch points from our 12 participants here. As we can see, these touch points clustered across these crosshairs, but still we see some variances. That's because first, the tracking inaccuracy, and also the user error. And finally, different users have different body, thus different offsets. Now we draw 2 sigma ellipses here. In this case, smaller ellipses indicate higher accuracy. We calculate the diameter a button must be in order to achieve 97.5% accuracy. Here's the result. The result indicates that SkinTrack needs a button size, average button size of 21 millimeter to achieve this accuracy. Luckily, previous work also used this evaluation, so we can easily compare SkinTrack with them. One result shown in blue is from OmniTouch, which is a computer vision-based system. As we can see, our result is about comparable. Also, House et al. Report a similar result, that a capacitive touchscreen needs a 15 millimeter button diameter to perform accurately. Remember that we collected 3 testing rounds after the band was reworn by the user. The reason we want to do this is because we found most biosensing systems don't work at all after they are taken off and put back on. Almost all systems need to be recalibrated each time it's worn, which is clearly not ideal. Here is the result for SkinTrack. So we can see the button diameter increased from 21 millimeter to 32 millimeter, which is just not as accurate, but still it works. We also run a series of supplementary evaluation for SkinTrack. And I'm going to go through this result very quickly. First, we doubled the density of the crosshair from 30 millimeter interval to 15 millimeter interval. And in this case, a bigger circle indicates higher error. As we can see, the touch points farther away from the wristband has higher tracking error, which is predicted by our theoretical model. Also, we evaluated SkinTrack to detect the discrete finger touches, and the result showed an accuracy of 91.8%. We also evaluate SkinTrack when there's a thin clothing between the finger and the skin, and it shows no significant difference between the 2 conditions. Also, skin moisture doesn't have any significant effect on the touch tracking accuracy. We even put the ring on a different finger. Here, we put the ring on the ring finger and still use the index finger to touch, and there's no significant difference between them. With this 2D tracking ability, we propose some interaction modalities based on top of that. So just to remind you what SkinTrack can do, here's a video shows SkinTrack can detect hover, touch, and even it works through a thin clothing. Now, with SkinTrack, we can support directional swipes. We can detect discrete touch positions. Also, 1D slider will be a piece of cake. Finally, it supports continuous finger tracking. Like many sensing systems, SkinTrack has limitations. For example, the major obstacle comes from the sensing stability across time. We saw the touch tracking accuracy decreased over time, And to solve that, we hope to use longer training process, superior electrode materials, and band ergonomics. Also, for the power consumption, remember that this ring can be used for 15 hours. It's quite long, but it emits a signal once it's powered on, so it's a constant signal. In order to reduce the power consumption, we can reduce the duty cycle, or we can even dynamically emit the signal only when it detects the finger is touching on the skin. And finally, we found the physical contact condition between this finger and the skin can affect the reported position. In order to solve that, we hope to develop a superior receiver filter on the receiver side. And also we can try different frequency on the emitter side, or even combine different frequencies for the emitter side. I want to conclude with some example applications. So to show what we can do with SkinTrack. Here, with SkinTrack, a user can navigate through a list of applications. It can select by a right swipe. In this list of music, user can scroll up and down and confirm by right swipe. We can create shortcut on the skin, for example, by dragging icons onto the skin, and then do a quick launch by simply touching on the skin. We can even play Angry Bird, which you know how hard it would be if we play on this tiny little screen. Also, we can use our backhand as a number pad to dial a phone number. Lastly, we can use SkinTrack to support spatial gestures. For example, we draw N to quick launch a news app, or silence a phone by drawing an S. We draw an A to quick launch an address book. Here, we can scroll normally on the screen, or do a rapid scrolling by touching on the skin. Thank you for your attention. I'm happy to take questions.
So thank you very much for this presentation. We have time for 2 questions. Do we have people who want to ask questions? Yes.
Excellent work and excellent presentation. You talked a little bit in your study where you had to take the band off and put it back on. Did you also have to take the ring off and put that back on as well? Because you talked a little bit about the stability over time and the session dependence. So could you answer that question, then talk a little bit more detail about how you would address the session dependence?
That's a good question. So in the user study, we didn't take the ring off. The reason for that is because we didn't find any influence if we take the ring off and put it back on. But the major obstacle comes from the reward of the wristband. So that's the most important thing we want to evaluate. And also how to solve this like instability across section. For now, we use like a mylar layer between the electrode and skin, so that ensure only a capacitive coupling between the electrode and skin. That makes our system more immune to like the humidity change across skin. But yeah, definitely more work should be done to solve that instability over time across user or across different reward condition.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I'm curious if the back of hand performance changes if you bend your wrist, so it's no longer in plane with the ring or with the wristband.
It affects a little bit, but majorly comes from the contact condition between the electrode and the skin. Also, it changes the path, the distance between finger touch and our electrodes. Again, I think one way to solve that is just like the regression model or machine learning models being exposed to different contact conditions, and then it can be more robust across time.